Okay, so it is necessary to understand the masks required for CMOS device fabrication. Of course, it is a number of masks are also very essential um, for to identify how much advantageous a particular technology is. So most of the cases we are trying to reach how many number of masks, the less number of masks that should be required usually. Okay, so in that sense, let us consider how many masks that we have used in our CMOS fabrication in this particular example. So we have considered the annual process, right? So in this annual process, how many number of masks we have used? That's what we look at now. Okay, so knowingly, unknowingly, that we have mentioned the masks at different places. Wherever the photolithography process is there, we had defined the mask, right? So now let us consider one by one where exactly we have used the masks. The first mask is mask number 1, for example. So mask 1. So mask 1. So where the mask 1 is used? Okay, mask is nothing but a glass plate, as you can see here. So for example, you consider a device here, something like this. Okay, I want to create a one well here at this point. Okay, because I want to diffuse some material at this point, right, at this place. I want to diffuse some material at this place. Therefore, without affecting this area, this area, without affecting this area and this area, so only the dopants must be focused at this point only, from this point to this point only. In that situation, mask is required. Okay, so that means mask is something like this. So I will write the three-dimensional view of this one so that you can understand the point. Sorry, something like this. Okay, so this is a three-dimensional substrate, for example. So I want to mention only the mask at this the diffusions at this points only. Okay, n-type diffusion is only at this point only. So that means that this entire portion must be covered with some plate. Okay, this portion should not be exposed, right? So this portion should not be exposed. Only the exposed portion is whatever the open the window is there, that portion only, right? So only this portion only we have to expose. In that situation, we have to create one layer on top of it. Okay, so therefore this is the mask that we have to define. Okay, so in this mask what I will do is that, so only this particular portion of the glass plate, mask is nothing but a glass plate, we have to pattern stitched on it. Okay, patterns, we have to place the patterns on it. So whatever the directions that we want to do, we can do it here. So that means that, so this portion is entirely covered with, this portion is, and I can write it here. So this entire portion is covered with black coated surface. Okay, this portion is entirely covered with black coated surface. So only the transparent portion is this much. Okay, so therefore, so that is the reason why whatever the material that is available at the top of this one, whatever the material that is available on top of this one cannot be affected by using this particular mechanism. So therefore, we will send the UV radiation, everything, and we can open the window, we can diffuse something at this point. So in that situation, other portions cannot be affected. So therefore, this is called a mask. This is called a mask. Okay, so therefore different type of masks that we can see depending upon what kind of material, what kind of portions that we want to expose, right? So therefore you can easily understand the mask one that we have used for the N diffusions. For the N diffusions we have to use this one, right? N-well formation we have to use this one. So this is the one mask. Mask one is this one. So therefore, what is the mask one here now? Mask one is meant for formation of well. Formation of well. Is it clear? Is it clear? Okay. Now, next let us go for mask number 2. So, mask number 2. So, mask number 2 is nothing but once the diffusion takes place, okay, I have diffused everything there, okay, there is no problem here. well is formed here. Now again what I have to do, we have to cover the entire region with the field oxide. Okay, so we have to remove the field oxide entire thing and form the gate oxide. Is it right? So our requirement is that something like this. We have to create a only at this portion gate oxide is required. So therefore the patterns must be etched for this particular portions only. For this portions only, right? That means we have to form a gate oxide on top of it, and we have to pattern the gate oxide. We have to keep the gate oxide only at certain portion, and we should not be there in other portions. That means something like this. For example, this is what we have a substrate. We have formed the gate oxide on top of it. It is a gate oxide. Now gate oxide is required only at this portion, right? Only at the middle point only the portions are required. That means that I have to create a one mask there. I have to coat it the entire portions of some portions of this one with one color, black coated colors and something like this. So this is another mask. Are you agree with me? Is it clear to all of you? What do you mean by mask here exactly? Please, someone has to respond. What do you mean by mask? It's nothing but glass plate, some patterns etched on it. Okay, somebody please respond in chat box.
Sir, is it like a protective layer?
Yeah, exactly. It is like a protective layer. Actually, there is a small difference is there actually. The protective layer is nothing but on surface, whatever the material on surface, the question I have given, the passivation, that means that we have to cover the entire region with the field oxide, right? So something like this. So we have to cover the entire region with field oxide. So for example, silicon dioxide I can provide this one. So this particular silicon dioxide can be considered as a protecting layer for this particular substrate, right? This is the protecting layer for the surface. Okay, so therefore this is the passivation layer actually. This is a passivation. So therefore silicon dioxide SiO2, SiO2 can be called as passivation layer to protect the surface, whereas the mask is meant for whether we want to send the light through that one or not. That will be decided by the mask. Of course, I can say this is also indirectly we can say that the protective layer only, but it is not on the surface. It is on the one particular photolithography machine is there. So we have to insert this mask in that one, and that will be projected on that one. Okay, here is the one device will be there. Okay, so we have to insert the mask over there, and this device consisting of light projection over there, and this light is exposed through these particular transparent portions, right? So that video also you can observe from the video also. It is just like the Xerox machine. You can see that no light is exposed on that particular surface on the object, and that object will be projected on the white paper. Okay, something like that only. Fine. So therefore, yeah. Any doubt related to this? So this is the mask. So the mask number 2 is meant for what? Mask number 2 is meant for, as you can say that, gate oxide. For gate oxide. So this is also called as thin oxide. Thin oxide. It is also SiO2 layer only, but oxidation thickness of the oxide, purity of the oxide is different than that of the field oxide. Okay. So therefore mask number 2 is meant for this particular gate. Okay, gate oxide. And the third mask is required, mask number 3. Polysilicon deposition. So you can see here we have placed the polysilicon on entire surface, right? On entire surface we have created the polysilicon. But the polysilicon is required only at the portions of this, at the middle, on top of the gate oxide only. On top of the gate oxide only we have to use the polysilicon, right? So that means that we have to create some pattern on a mask. Okay, so that means the mask is required. So that mask is, we can call it as mask 3. Mask 3 is meant for polysilicon. Polysilicon formation. Clear? Okay. Next one is mask number 4. Mask number 4. So in the mask number 4, what we have done, okay, we have created the gate, we have created the oxide. Of course, the oxide and all these things are absolutely available here. This is the imitating this is a field oxide, okay, covered with field oxide. And now I have to create a mask for what I have created here first, source and drain. Okay. So I have created the mask for this particular one, right? So the creation of n plus and n plus of the n well, right? So therefore mask number 4 is meant for, okay, so n plus diffusions. Actually ion implantation techniques we have to n plus diffusions. N plus diffusions where we are using source comma drain of NMOS transistor, okay, the substrate of PMOS transistor. Please remember. So in that situation, n plus diffusions we are using. Sorry. So for n plus diffusions, what we have to do? Yeah. So we have to do say n plus diffusions. For n plus diffusions, we have to create a mask over there. Okay, we have to create the patterns on it, patterns on top of it. Or indirectly, or another way that we can also do it. So instead of saying this one, so meanwhile what we are doing that whenever we are doing these particular exposures, we have to create another mask that is for P plus mask. So exclude, that is the glass plate that we have to use for the to protect the layer for P plus region. So the P plus regions we need to mask the other inter regions. Okay, so that means this is actually whatever the mask that we are talking about, this fourth mask, that is called P plus mask. Please remember, we have to call it as P plus mask. Right, so name they have given, that's it, nothing more than that. Okay, next, mask number 5. The same thing that we have to consider. Okay, so the same thing we have to consider. Okay, copy. So instead of n plus, what we are doing here? N plus, we have to use P plus. Okay, so it is a PMOS, it is NMOS. So what is this mask we can call it as? It is n plus mask. It is n plus mask. Okay, this n plus mask we normally call it as mask 5. Okay. Next mask is, okay, the mask number 6. So therefore the contact cuts are required. For example, so everything is cleared, everything is formed here. So we have a gate, we have a polysilicon, we have a gate, we have a polysilicon, we have a source, we have a drain, we have a substrate, of course, sorry, well is also here. Here is the substrate, source, drain. Okay, after completion of this one, we have to cover the entire region with the field oxide. Entire region must be covered with field oxide. Okay, entire region is covered with field oxide. Now what I have to do, I have to create the portions, some portions like here. So one portion is required, one portion is required, one portion is required, one portion is required. What is these things are called? Contact cuts. What we can call it as contact cuts. Okay, so for the contact cuts, one mask is required. That means selecting a particular portion for contacts. Okay, so therefore we have to create a mask for contact cuts. Contact cuts. We have to create a mask for contact cuts. So these are called contact cuts. That means we have to create a glass plate and pattern switched on it. in a particular portions that need to be exposed, or those portions need not to be exposed, something like that. Okay, so mask number 7. So we have another mask that is called mask number 7. So mask number 7 is meant for metal deposition. So for the purpose of metal deposition, where exactly the metals are required, okay, that portions need to be open. Okay, so therefore patterns are initiated, and we have to open the windows for these particular portions. We have to selection is one point, and removal of this particular portions is also one mask is required for that. Okay, so that is called in order to open the window for contacts. Open the window for contacts. Opening the windows for contacts. Last and final one is we have to mask number 8, that is cover the glass plate. Cover the glass plate on the other portions of contacts. Other portions of the contacts. Okay, so therefore in order to create, of course this is the generalized view actually, so in order to really, if you want to fabricate this one, more number of masks are required, but anyway, so simplest manner we can consider that 8 masks are required to fabricate a NMOS device in this particular context. Okay, so please remember that one. So these masks definitions I did not mention here in this previous lecture, because it's very difficult to manage all those things. Now it is you understand, if you want to open the window for this one, mask is required. So on that mask we have to pattern stitched on it, so that the light, whenever the light is exposed in a transparent portions, that particular material property will be changed, and we can easily remove the portions in order to access that portion, access that particular area. Okay, that's what you have to remember. So this is what we normally look at this one. Now, so I hope yesterday I have given the homework, you might have completed that one. Another one is twin-tap process. I want to do it. So very quickly, only 2 steps are additional to the existing circuit, the existing fabrication steps. Okay, so let me go for twin-tap process. Okay. So twin-tap process, twin-tap process. Okay. So actually, if you are using the NWEL process or the PWEL process, any one of the device or any one of the transistor performance need to be compromised somehow. Okay. So in order to avoid that one, and in order to constrain those devices in a single place in a absolutely the same size of the NMOS and PMOS, another method is there that is called twin-tap process. Okay, twin-tap process means here we need to accommodate both transistors at the same, placed at individual wells. So very important one. So individual wells is the important one. Okay, please remember that. What does it mean? That means I have to consider, for example, I am going to consider N substrate. I am considering N substrate, right? See, what is the additional step? Let me write here. So N substrate I am considering. Okay. Now I have to consider another type of same material on top of it. I have to consider same type of material on top of it. So this is called epitaxy. what we can call it as epitaxy layer formation. So what do you mean by what is the type of material for epitaxy? This is also n-type material. Epitaxy is nothing but epitaxy material is also n-type material, but the dopant profile of substrate and epitaxy will be different. Okay, if it is n substrate is a lightly doped one, it should be moderately doped one, something like that. Okay, so therefore doping profile difference will be there between the epitaxy and n substrate. That's what you have to remember. Okay, in that situation, it allows us to create two wells individually. Okay, so that means that I can create n well. So I can create n well here. I can create n well here, and I can create p well at this point. Normally, this is meant. This is used for the purpose of avoid the latcher problems and all other things. We will discuss that point later on. But this is an approach that we have to use. So without epitaxy, it is not possible to create the two wells. Okay. So therefore, this is how we have to do this one. So how many layers that are required now again? So epitaxy doesn't require any kind of additional mask. Actually, epitaxy is required on the entire surface. Whenever the things are required for the entire surface, no mask is required. Okay, directly we can expose it to the wafers. Now the mask is defined for both for n well and p well. Only one mask is sufficient for that one. Okay, therefore there is no additional steps are required for this one. Okay, just whenever we are digging the n well, okay, so we have to create a pattern on the same plate. I have to create a pattern for the p well also. That's it. Okay, and remaining everything is same. Okay, just only what we have to do, we have to create the gate oxide on top of it. Yes, I am going to create a gate oxide, and gate oxide on top of it we have a polysilicon. On top of it we have a polysilicon. Okay, and for n well, for this, let me consider this is called p well. This is called p well. This is called n well. This is called n well. So in the n well, what is the suitable transistor that I can form? N MOS transistor, n plus. The suitable substrate is p substrate. At the same time, here also n plus is required for substrate. Similarly, for a PMOS transistor, p plus dopants are required, p plus dopants are required, p substrate is required for this one. Now I have to cover the interior region with, sorry, I think I have to use this one. I have to cover the interior region with field oxide. Please remember that is a field oxide. So this interior region is covered with field oxide. Now only the mass, only the contacts are required at these portions only. So only the contacts are required at this portion. Contacts are required at this portion. Contacts. Okay. That's it. So this is called twin-tub process. Only the additional step is epitaxy layer formation is one thing that we have to remember. Okay, so please remember these processing steps. Okay, so with this we have completed the CMOS fabrication. The three methods. One is N well, P well, and twin-tub process. Okay, so any one of the question is guaranteed in your main examination. So please go through the steps, individual steps carefully, and watch the video whenever you have a time, so that you can write some statements properly, so that the 12 marks question they are giving in the main examination. Okay, you please try to understand. So NMOS fabrication or CMOS fabrication, compulsory either 6 marks or 12 marks question you will identify, you can see in your main examination. Okay, please don't forget to learn this particular thing. Okay, now let us go for